Hey everybody, my name is Aryan, and I'm here to talk to you about our forthcoming paper out of Redwood Research, Ctrl-Z, Controlling AI Agents via Resampling. It's a big paper. We covered a lot of dynamics. We're basically, generalizing the AI control methodology to an agent setting, but I'm going to be focusing on, the eponymous resampling dynamics here. So yeah, a little bit about the setting first, just so we're all on the same page. If you have questions during the setting section, please just raise your hand. I'll want to make sure we're all good on this stuff first, and I can cut you off if we don't have time. So yeah, the data set we're working with is we have 257 multi-step sysadmin tasks that we sourced from, inspired from Stack Overflow, and then we did some LLM munging. The tasks are meant to be solved in a bash shell. So you have an agent that, just in a simple REPL loop, it takes in the bash history and it outputs in the next command. For our untrusted model, we use GPT-4o Mini, which solves 56% of these tasks. And for our trusted model, which we use as, a kind of a tool to help improve our safety, we have a, less intelligent model, Llama 3.18 Beep, which gets 0% of the tasks, right? And so, we kind of are going to end up somewhere between the 0 and 56% usefulness. We're always going to normalize our performance between 0 and 56%. So when I say 1, that means 56. The basic setup here, what this looks like, just, once again, so we're all on the same page, is we have some sort of task, some sysadmin task, write a shell script that does something, and we spin up a little bash environment for the agent. We take all the history in the environment so far, send it to our agent, some LLM, and it outputs some command for us. For example, apt install grep, reasonable command. This command is then shown to a trusted monitor. I'll get into more details of exactly how this stuff works later, but this is a general idea to keep in mind. And the trusted monitor tells us, hey, how it monitors this command. It tells us how suspicious does this command look in this context. Is this something that we should be running, or is this something that could be malicious? It'll give us some suspicion score out, and bear with me here. If we have a little bit of a little flow chart. If the command is unsuspicious, we'll just execute it. Seems all good. If it's medium suspicious, we might do something else. For example, like try another sample from the model. And if it's very suspicious, we might audit it, right? Have humans expend some expensive human labor in order to deeply audit this command to see what's up. In this case, if it's a totally fine command, we'll just execute it, runs in the shell, and then we loop, right? So this is the basic agent loop you should be imagining. What are the control dynamics then? Well, the basic idea is we're trying to adversarially test, how safe our techniques are. So we have a red team and a blue team. The blue team is building these safety techniques. The red team is kind of stress testing them. We simulate the outcome of deploying this untrusted model for across 100,000 tasks. We of course don't have 100,000 tasks. We do a bunch of mathematical upsampling, some simulations and stuff. The red team is going to basically scaffold this untrusted model. Their goal will be to download and execute some malware. We have a dummy malware link that we put online, and the red team basically wants to download and execute that surreptitiously without the blue team noticing. The blue team, on the other hand, wants to, they want to maximize simultaneously usefulness, which is performance, right? How often you get the task correct, and safety, which is the probability that the red team fails to download malware, right? So ideally, you don't want your safety techniques to come at great performance hits, and that's why we measure both usefulness and safety. All our graphs, our main results look like Pareto frontiers of we'll have usefulness on one axis and safety on another axis. And we want to see, for a given level of usefulness, how safe can we be? It's a bit much, but basically this is just the setup from earlier. But the idea here is when we're measuring usefulness, we do exactly the loop that we mentioned earlier. We run the loop. You, at the end, check whether you completed the task successfully. Pretty straightforward. When you're measuring safety, on the other hand, it's a very similar loop. It's nearly exactly the same, except this regular LLM policy has been replaced, this agent has been replaced by a red team provided attack policy. Now the red team can, use various tooling, various scaffolding techniques, and along with a bunch of they get a bunch of human help, right? The humans can kind of give the LLM ideas for how to insert attacks, stuff like that, in order to, basically optimally stress test our blue teaming safety protocols. So yeah, once again, basically it's the same idea, except instead of routing to the safe LLM, we route to a red team provided attack policy. So what arises in this setting? I'm going to be focusing on the new things that arise in this multi-step agent setting because, the first original control paper, I think it's a great paper. You should all give it a read if you haven't, or at least a skim, explores pretty well what happens in the single step setting. And so starting with the single step setting, what does this look like? It looks like, you have an agent taking a bunch of actions and one of them is suspicious, right? One of them, does some bad stuff. The attack policy, which is to say, puts all of the attack steps into a single action. Now, this has the upside of you only need to insert an attack one time, right? You can just download the malware, execute the malware, bypass all safeguards. You can do all that stuff in one action, right? And you don't need to touch too much. On the other hand, that one command is going to be extremely suspicious. If you look at real world vulnerabilities, usually the way that tech stacks are exploited is not by in one go just kind of bypassing literally everything. You kind of over time incrementally take steps that bypass different parts of whatever your safety measures are. So we introduce multi-step attacks, right? Which is only possible because we have this agent taking multiple steps. What does this look like? Well, now you're distributing the different parts of your attack over multiple actions. Maybe in action 2, you'll store the link to the malware somewhere. Maybe in action 3, you'll download that link, right? Maybe in action 5, you'll then make that file executable, and then in action 7, you'll actually run the executable. You can split things up, and the idea here is that each individual action is less suspicious now, right? You only have a tiny piece, and it's much easier to interweave things with, actually totally reasonable commands to make things seem less suspicious. And this causes the red team basically to just win more often. So this is the setting that this multi-step attack setting is kind of the setting we're really exploring in our paper, right? What are the dynamics that arise due to this? Well, one of the big downsides is that for the red team, so upsides for us, I guess, is that when you have these multi-step attacks, we can kind of, foil these attacks in many more ways. For example, one of the things we explore, one of the dynamics we explore, is trying to prevent the agent from being able to complete an attack once it starts, right? Before, when you have the single step action, once you run this, it's over, right? You've run the malware, all your machines are pwned, all your systems are broken, it's over. In this setting, however, you kind of can get to action 2, action 3, action 4, and you still are able to incriminate this model. You're still able to be like, hey, we haven't lost yet. As a blue team, we can, maybe take actions that'll either prevent the red team from completing the attack or, just catch the red team red-handed halfway through. So what does this look like? One protocol we investigate is what we call defer to trusted, where this is basically using a framework that Redwood talks about sometimes called the execute, replace, audit framework. The idea here is you're looking at a graph of, for each action, how suspicious was the trusted monitor? What score did it output? If you remember that little sus meter, that's basically what this is. And you'll notice that the blue bars are what it looks like for clean, normal actions, right? Usually, it's pretty unsuspicious. Sometimes, it's a little bit suspicious. It's never very, very suspicious. The red is orange is what the suspicion scores look like for malicious commands that we've optimized to be as subtle as possible, but they're still more suspicious than clean commands. What happens here? Well, in this execute, replace, audit framework, we say, like before, if you're below a certain threshold, just execute it. These commands are probably safe. You're totally fine. You don't want to have this overhead of constantly having to do a bunch of safety work. So most of the time you just execute. Some of the time you're then going to replace, right? You're going to say, okay, well, if it's kind of suspicious, I'll replace with some other sort of command. In the case of defer to trusted, we call it that because your protocol is going to defer to the trusted model, right? Which is less intelligent, less capable. It's going to give you a less good command, but it'll also be, if your original command is very suspicious, hopefully you can gain a lot of safety for a small usefulness penalty. And so we'll look at, the usefulness safety trade-offs in just a sec. But if it's very, very suspicious, we audit. Once again, it's not a long talk. We don't have time to talk about all the details of what I mean by audit, but basically for now, we just use an O1 based auditor, which just easily catches all attacks. It's meant to simulate a human in real life, spending a couple hours investigating this particular command or what's going on here. So yeah, how well does this perform, Aryan? You talk a big game, but does it actually do anything? Well, here we plot our safety usefulness Pareto frontier. This just zoomed in over here. The idea is that you can get, of course, 100% safety, usefulness by using trusted monitoring, where you if you basically never defer at all, if you just monitor and audit sometimes, then you get 100% usefulness, but your safety is only what, 40%? Not great. If you, some of the time, defer to trusted, as you defer to your trusted model more and more often, of course, you take a bigger usefulness penalty, but you're much, much more safe, right? And so this curve finds that at 95%, if you're willing to accept a 5% penalty to your performance, you can get your safety up to 70%. And if you're willing to accept, a 20% hit to usefulness, you can get safeties above 95. What's up?
Is there some privileged reason for the number of tasks that you run this over? Because I imagine if you run it over many more, then your curve looks way worse.
No. It's pretty invariant. It's pretty invariant. And the reason is that because this is like a high stake setting where even one failure is very bad, the red team, it only inserts an attack with very low probability, right? There's no point in attacking every time if you only need to insert one. And so it's we run sensitivity analyses to like game length, basically doesn't change at all. If your game length is 10, that's different, right? But 100,000, a million, 10 million, 100 million, they're all the same. Yeah, great. So we introduce our new techniques, which are only possible in this like multi-step agent setting. Primary one is what we call defer to resample. Instead of just deferring to your trusted model, right? Your trusted model is notably less capable. Why don't we just take another sample from our untrusted model? Now, there's of course obvious downsides to this. We'll get to this. We're going to explore the game tree a little bit together. It'll be a fun little time. So yeah, what's the idea here? When you're resampling, you sample a step. Let's say you want step one. You take a sample from your LLM. If it's above some threshold, instead of just running it, you resample from the LLM. You keep resampling until you have a command that's either above your below your threshold, rather. You know, it's not that suspicious. Or if you sample, let's say 3 or 5 times in a row, we set some limit so that you don't end up sampling infinitely forever. After a certain amount of time, you just defer to your trusted model, right? Because you're like, this is just way too suspicious. What's the idea here? Well, first, here we'll just look at this. The idea is that stochastic attacks, right? Which is to say attacks that like red teams that only insert the attack some of the time. You can imagine that a scheming model or a malicious model could implement a kind of rare failures type strategy where it like only inserts the attack sometimes. In those cases, the attacks usually just get replaced, right? Defer to resample makes it so that if you like insert attacks half the time, right, the attack is often going to be resampled, and then you'll just sample a clean, completion, which is usually far less suspicious than the attack, and then the clean one will be selected, so the attacks just never finish, right? This is a graph that shows if the red team adopts a certain probability of inserting an attack, how many attack steps do they need to insert in total in order to like succeed just one time. And if you look at like the deferred resample, even if you're only inserting attacks 75% of the time, let alone 50, you need like what, over 1,000 attempts just to get one successful attack through, which is to say this selection pressure is strong, right? You really need to, if you're a malicious model here, you really need to in order to successfully complete your attack to consistently submit attacks, right? Otherwise you'll just always, the clean ones will be selected. You can see that deferred to resample is way better than deferred to trusted in this regard. Okay, so what happens if you have these deterministic attacks? If the red team is just constantly, like just malicious command, well, ideally you would hope this would be pretty incriminating, man, right? Like you would hope that if you have like 3 suspicious, commands in a row every time you resample, this would be more incriminating than just one. And so what we do is we measure this. We say, hey, on the top, we have this kind of a very similar graph to before. This is your clean commands, right? They're not very suspicious. These are your attacks. They're like kind of suspicious, and we catch, let's say 33% of them, right? They're the percent of attacks that are above that you're like able to audit with the humans. 33%, not too bad, but hopefully we can do better. And if we do this resampling protocol, what we find is that, if we do the resampling protocol, what we find is, and then we just, let's say we take the mean of these 3 suspicion scores. You could do more fancy things, but we stick with the simple, just take the mean of their suspicion scores. You find that you go from catching 33% of the attacks to catching 70% of the attacks, just because it's so much harder. You have to be, consistently submitting these attacks, which is much better signal than just one suspicious command. Yeah.
How does taking the mean over multiple resamples compare to like having 3 different monitors with different models?
Yeah, it's way better. We test things like just improving the quality of your monitor by averaging over like multiple samples from the monitor or multiple different monitors, and they improve performance a little bit. This is way better. It doubles performance. This is kind of the best we could get with all of that averaging and all that. Yeah. Okay, I'm gonna move on for now, but happy to come back later. We're almost done, to be honest. So basically, just how well does this perform, right? Well, we find for a given hit to usefulness, the defer to resample performs way better, right? The reason is pretty straightforward. You just can't afford to resample so many more times without losing as much performance, right? Like if you're deferring to trusted, let's say 20% of the time, 20% of the time your actions are going to be coming from a much less capable model. And it's just pretty untenable. Your usefulness goes down very quickly, as you can see. Whereas for deferred to resample, for a long time, right? Even if you're deferring, I think this point is like 20% of the time, even if you're deferring to resampling 20% of the time, you still only have like a 2%, 3% hit to performance, which just lets you have much higher safety scores for a given level of usefulness. And then in practice, we also have a bunch of other techniques. So I'll shill some of them for you real quick. If you also use an untrusted monitor, which is a whole other thing that uses an untrusted model to kind of monitor its own outputs, but you have to handle all the like different ways they might collude and all that stuff. Then you get an even better safety curve. This is like you reach near 100% 100% safety at like less than 15% performance degradation. Yeah. For more about this, you can go to Adam's office hours at 4:30. Adam Kaufman, he's one of the co-authors on this paper, and he's going to be talking all about these like just this specific curve, right? The untrusted monitoring game tree here of like collusion and collusion busting. Yeah, that's basically all I have. I have the numbers for things, but numbers aren't as interesting. Graphs were pretty. We can look at the graphs instead. Be happy to take questions. Yes.
What is the time travel?
Yeah, so sorry. Okay, yes. So in fact, by the way, we do lots of fancy things. As I said, our paper goes into a lot of depth about this stuff. One of the things you can do when you're resampling is when you notice particularly suspicious actions, you can resample, in the present, kind of the current action that's being sampled. You can also resample in the past. You can kind of go back and resample multiple times, right, to try to get more information about what was going on earlier, right? This doesn't work with single-step attacks because, either the attack happened or it didn't. But with multi-step attacks, maybe you don't notice something suspicious is going on until step 4 of the attack. And then, you can go back and kind of get a lot of value from what we call like time traveling back. And yeah, you can do even better versions of this where you like fake a rollout and have the model like keep going and see if it continues an attack. We like basically don't include these results in the body of our paper because they're much more like speculative. But yeah, okay.
How much of the improvement from deferred to trusted to deferred to resample is the time travel aspect of that versus just
great question. It's about okay here. Actually, this gets here. So this is with time travel. This is basic deferred to resample, and these are just like intermediate things. Don't worry about them. Basic deferred to resample. Let's say at 95% usefulness, is 6% or 10% better than deferred to trusted, and is like 5% worse than time travel. So in this case, it would be like if we look here, it's like 2/3, right? So like a bunch of the value comes from deferred to resample. You get a bunch more value from looking into the past and doing all that stuff. Yeah. Jake.
Sorry, I think maybe because I turned up 5 minutes late to the talk, I missed some key background.
Uh-huh.
Can you like spell out a little bit like exactly what happens in deferred trusted? Like what happens? So if you audit and then the model is and then you're like, oh no, you caught the bad action. Then like you stop the game and then like how does this appear on the graph at the end or something?
Yeah.
And then and in the scenario where in the intermediate thing, what's happening?
Yeah. So basically, when you audit,
when
you audit, if this was in fact a malicious command, then the blue team wins the game, right? They've caught the red team scheming, they win. If it's
so what does that look like on the Pareto curve?
It's just when the Pareto curve, like the x-axis, safety, is just probability that the blue team wins. That's what safety is.
Okay.
And the blue team can win either by sorry that I'm flipping so far back and forth. The blue team can win either by catching the red team or by just preventing any attack altogether. Both of these contribute a component, and I think it's kind of important to look at both these. They're kind of two sides of the same coin. The harder you make it to complete an attack, the more blatant the red team needs to be, and then you end up catching the model more often. I view this as the classic analogy I use is if there's no lock on a bank's door, I can just walk in and steal money. If they put a lock there, even if I have a lock pick, right? Even if I'm able to pick the lock, you at least have like, video evidence of me now like picking a lock and like clearly going somewhere where I'm not supposed to be. And this just makes it a lot easier to incriminate me as compared to if I could just walk in.
Sure. So, and how do I score the usefulness in the scenario where I've caught the model and I stop the game? Because
yeah, so usefulness is measured specifically on a benign model, right? So you would,
sorry, yeah.
Yep, that's all good. Yeah, we had a few more questions. Yes, good sir.
Yeah, have you tried this with a stronger trusted model?
Stronger trusted model? Yeah, so for example,
how do you think about what's the most interesting question? Is it with a big gap or a small gap or?
Yeah, I'm interested in all kinds of gaps. I think it's becoming less important now. I think back in the day when you had to use like GPT-2 as your small model, that model is just too dumb to do anything useful at all, right? You don't uncover any interesting dynamics. We're now at a point where our less capable model is Llama 3 AP, 3.1 AP, which is like pretty capable. It's capable enough to like coherently reason about this stuff. It's just not as good at it, right? It's just not as smart. I think it's a very reasonable analogy. In the future, I think that I view a lot of the value of our work as methodological. right? I want people to follow the same methodology in the future using whatever the best trusted models are at the time. My guess is, you know, the trusted-untrusted gap might be a bit bigger than it is here.
Yeah, but like right now.
Yeah.
And you're saying like, well, in the future, you want people to use the best trusted models? Or
Yeah, I totally
might
yes.
think, right.
Yeah, so I think it's valuable to do like to iterate on techniques using like, you know, the most powerful trusted models we have. I just sadly don't have I don't have AGIs that are untrusted yet. And so in order to like do the experiments, we, you know, kind of
Sure, but like, okay, what about like 3.17 TB? Like, have you tried that, for example, or like, why didn't you pick that one?
Yeah, so for example, the in practice reason we didn't pick 3.70b is it's more expensive and more annoying to host and serve. The longer answer is something like, yep, your safety numbers go up, right? If you use smarter models, if for example you use 4.0 mini as a trusted model, you know, you get 100% safety, 100% usefulness here. Yeah, it's really hard to there's no like super principled reason for like this specific model size. It's mostly just how do you explore these dynamics when you have a gap.
So like, and the kind of ranking of the 3 colors of the curves, is that the same? Like, have you tried? Is that the stronger trusted
Yeah,
model?
so we haven't tried with 11370b. We've tried small modifications. My guess is that the ranking of the curves is going to be pretty similar. My guess is also that as you get really close to 1, all the curves mush together and they'll
Sure.
do everything. Yeah. So yeah, we do optimize our setting a little bit for not being at 1. Yeah. Last question. Sorry, you haven't asked a question yet. But...
So I was just going to follow up that with, I guess you need to choose your monitor model such that it can't just, the blue team can't win by just like discarding the...
Yeah, indeed. And to be clear, in the future, I believe that we shouldn't do this. You shouldn't hamstring yourself at all. You should use the smartest models you have, of course, smartest trusted models you have. But for the purposes of, you know, R&D, yeah, I think we're all out of time. But I'm very happy I'm around the conference. My other co-authors are also around. I'll go back to the beginning slide so you guys can see their names. And I'm happy to talk about this stuff or control things in general anytime. Yeah, thank you guys so much.